Nothing beats. This is a video in which we will introduce the concept of an antiderivative. Let's take a look. All right, let's just start with this situation. Given a function, call it f of x, and say that that function f of x is actually the derivative of some other function, big F. So big F prime of x is equal to f of x here. The question is, can we find a function, big F of x, so that the derivative of this function, big F of x, that we're looking for is equal to this other function, little f of x? So really what that's asking is, given a derivative of a function, can we come up with the function for which when we differentiate, we get its derivative? Where did its derivative come from? Which function? That's the question really being asked here. Let's just consider this situation. Consider the function g of x is 3x squared. Right? It's a nice function. Then, can we find a function big G of x which satisfies the condition that the derivative of big G, g prime of x, is equal to little g of x here? Again, that's equivalent to asking which function big G of x has a derivative equal to 3x squared. Well, we might be thinking, oh, one such function is big G of x is x cubed, as if I differentiate x cubed with respect to x, I get 3x squared. So in other words, here is my function, little g, and that is the derivative of big G. And thus we found one such function that does this. However, that's not the only function. Consider another function, big G of x, which is x cubed plus 1. Notice that big G prime of x here is also equal to 3x squared, which is little g, because the derivative of 1 is just 0. So it should be telling us that there's not necessarily one unique function in this situation. Or even consider another function, big G of x equal to x cubed minus 8. This also works because big G prime of x here is still 3x squared, which is little g of x, another such function. And you think, well, what other functions could they be? Or in general, we could come up with big G of x is x cubed plus some constant, where c is just some real constant. And that is, if I differentiate big G here with respect to x, so g prime of x, I'm always going to get 3x squared, which is little g of x. So this is bringing us to the idea of an antiderivative. It's the motivation. The definition of an antiderivative is as follows. Given a function big F of x, we say that this is an antiderivative of another function little f of x on some particular interval I if the derivative of big F is equal to little f for all the values of x in this interval. So an antiderivative, and a key word here is an antiderivative, meaning it's not necessarily a unique antiderivative, if we can find a function for which when we differentiate, we get the derivative. So let's kind of think about it as the backwards process of differentiation. If we're given a derivative of a function, can we find the function for which it came from after the process of differentiation? So for example, just to see another one, big F of x here equal to 1/4 x to the 4th plus 3, that is an antiderivative of f of x is equal to x cubed, since the derivative of big F of x here is equal to little f of x, right? So if I go ahead and differentiate with respect to x, big F, so that's the derivative with respect to x of 1/4 x to the 4th plus 3, guess what we get? We get x cubed, and that's our little f. So there's an example of a particular antiderivative of x cubed. Or, for instance, if I consider the function big P of x here, which is 2 times sine of x minus 5, that is an antiderivative, one particular one, of little p, which is 2 times the cosine of x, again, since the derivative of big P is equal to little p. So if I differentiate with respect to x, this function big P of x here, 2 sine of x minus a 5, guess what I get? I get 2 times cosine of x, which is little p of x. And hence, big P of x here, 2 times sine of x minus 5, is an antiderivative of little p of x, which is 2 times the cosine of x. So we can find particular antiderivatives, but as we were kind of hinting at before, we can also find an entire collection of antiderivatives. So general families of antiderivatives. Let's say that big F of x is any antiderivative of little f. So what's that mean? That means big F prime of x here is equal to little f of x over some particular interval, let's call it I. Then the general antiderivative. So we can say the general antiderivative or the general family of antiderivatives is the collection of functions satisfying the condition big F of x plus some constant, where we have c is some real constant. So in other words, if I go ahead and note that big F of x is just some antiderivative, any antiderivative of little f, and then I go ahead and differentiate big F of x plus some constant c, then I will always just get big F prime of x, which is always going to be equal to little f of x. So this is what we call the family of antiderivatives, or the general antiderivative, as it takes one particular antiderivative, say big F, and then adds a constant to it, or that constant could be negative, right? So we're just taking the same function and shifting it up or down by some c units here. So for an example of this, let's consider the function little f of x, which is 2 times x. Then, hopefully it is apparent that the general antiderivative of little f we can call big F of x, which is x squared plus c, since if I differentiate big F here, big F prime of x gives us little f of x, which is 2x. And so the picture that we're about to see helps us visualize this idea. So here is the family of curves. Now the red line that we see in the screen here, here's our function little f of x is equal to 2x, right? So that, of course, is the derivative of big F prime. And each of these blue curves is a particular parabola, x squared plus some constant. So if we kind of identify like this one right there, we can think of that one as just the function y is x squared because it's going through the origin. Think of that as x squared plus 0. If I differentiate that, I get the same derivative, 2 times x. And maybe the one right above that, maybe that's y is x squared plus 1. Differentiate that, you get 2 times x. Or go down below, maybe this one right here is y is x squared minus 1. And then y is x squared minus 2, and so on and so on. So when we find the general family of antiderivatives, or the general antiderivative itself, it gives us the infinite collection of curves such that all of those curves have the same derivative as when I differentiate them, we always get, in this case, 2 times x. So it's important to note, when finding an antiderivative of a function, there's not going to be a unique antiderivative unless, of course, there's some other conditions that are given, and we'll look at such situations in a later video. But for now, given a function, which is the derivative of some other function, it has infinitely many antiderivatives, a whole family of curves that have the same derivative function. So we can also talk about something which is called indefinite integrals. Now, the topic of an integral is a long conversation, and usually that's what's referred to as the second big topic in calculus. For us, though, we introduced the idea of an indefinite integral, which is really just a way to denote the process of finding an antiderivative family. So that is, an indefinite integral is just a way to denote the process of finding the general antiderivative or family of antiderivatives of some function f of x. So what is this notation? It's as follows right here. So here is, on the left side, there is what is called the indefinite integral of f of x. Okay, that's the notation. And really, as we can see, the result is the family of antiderivatives that we've been talking about, assuming that, of course, here f of x is some or an antiderivative of little f of x. So it's just notation. So what is this notation that we see on the left-hand side? An explanation of the notation here. Okay, so first of all, that kind of elongated looking S symbol, that is the symbol which is referred to right here as the integral symbol. It comes from further concepts which we're not going to get into in this video, but that is our symbol for which we call an integral symbol. Let me just rewrite here, integral f of x dx, so we see it. The function f of x within the integral is called the integrand, okay? And that is the function for which we say we are integrating. And in this case, it is the function for which we are finding the general antiderivative of. So we say, okay, we want to integrate a function, f of x, and then that dx finally on the far right, again, integral f of x dx here, that dx is the same differential we've talked about before. It is the differential in x, and it tells us to integrate with respect to x. And moreover, really that means the same thing as you treat that variable x as the independent variable. Just like when we saw d dx of some function, little f of x, let's just say, is f prime of x, right? That notation d dx means differentiate with respect to x, that same differential in the denominator. Treat the x as the independent variable. For our indefinite integral here, it means the same thing. Treat the x as the independent variable for integration. And so, we have kind of back and forth process here. If I differentiate, I get a derivative. If I integrate, I get an antiderivative. And you can think of these kind of like backwards processes, if you will. So that's the dissection of the indefinite integral notation. And just to see a couple of quick examples here before we finish the video. For instance, if I'm given the indefinite integral of 1 divided by 1 plus x squared dx, then that is the family of curves, inverse tangent function of x plus some constant. Again, why? Because the derivative with respect to x of the inverse tangent function of x plus a constant is going to be 1 over 1 plus x squared. So it tells us on the left-hand side here, go ahead and, if you will, anti-differentiate this function 1 over 1 plus x squared and treat the x as the independent variable, giving us the collection of general antiderivatives for this function. Or another example, for instance, the indefinite integral of 4t cubed dt is just t to the fourth plus c here. So right here, indefinite integral on the left of 4t cubed dt is t to the fourth plus c. And that is, again, because if I differentiate with respect to t to the fourth plus a constant, I get 4t cubed, the actual integrand in my integral, my indefinite integral. So in that case, we're saying treat t as the independent variable and find its general family of antiderivatives, which in this case is the family of curves t to the fourth plus some constant c. So there's our introduction to antiderivatives. This is a huge topic in calculus, and in the upcoming couple of videos, we are going to explore these a little bit more and get a sense of where this topic could really lead us. But until that next video, it is Math and Beats. Later.